Okay, so today we are going to complete Chapter 15, our last lecture of the semester. We have four topics left to talk about. Allylic bromination, the oxidation of unsaturated fatty acids, radical addition of HBr to alkenes, and then we'll conclude with a brief discussion, brief introduction to polymers. So if we look at an alkene such as propene that has an allylic carbon. Remember, an allylic carbon is an sp3 carbon that is bonded to an sp2 carbon. We can measure the bond dissociation energy for one of the allylic carbon-hydrogen bonds, and we find that it is 87 kilocalories per mole. This is weaker than a typical carbon-hydrogen bond. For example, if we had a tertiary sp3 carbon-hydrogen bond, the bond dissociation energy is 91 kilocalories per mole. So what these numbers tell us is that this allylic radical is more stable than a tertiary radical. So why is it more stable than a tertiary radical? The reason is that it is resonance stabilized. So that unpaired electron can be delocalized via resonance, and we would draw our half-headed arrows in this fashion. Okay. So we have two equivalent resonance structures where that unpaired electron or spin density is shared equally by two different carbons. We could draw a hybrid structure. We would have dashed lines, and then we would draw our lowercase delta indicating partial charge or partial spin density, partial radical character. So this would indicate, this hybrid structure indicates that the spin density or the unpaired electron is delocalized on these two different carbons. So because the radical, the allylic radical is one of the two products of the homolytic cleavage of this bond, the delta H, or the bond dissociation energy for that bond, is lower than it is for other types of carbon-hydrogen bonds, other types of sp3 carbon-hydrogen bonds, because we get a resonance stabilized radical. So this fact allows us to perform a reaction at the allylic carbon, a radical reaction at the allylic carbon that we cannot perform at other carbons. So it's selective for the allylic carbon, which makes it very useful. And this is the allylic bromination reaction. So we're going to use cyclohexene as our example. And if we use NBS, I'll draw the structure of that in a moment, but we've seen NBS before. It's a reagent that gives us a low concentration of bromine. If we do that in the presence of light or peroxides, remember peroxides are radical initiators, then we obtain a bromide where the substitution, the radical substitution, has taken place at the allylic carbon and only at the allylic carbon. Okay? So I'll draw the structure of NBS over here, and then we'll take a look at the mechanism of this reaction. So N-bromo succinimide is what NBS stands for, and it looks like this. We learned about it back in chapter 10 as a reagent that provides a low concentration of bromine. So let's take a look at the figure from the book. Whoops, right here. I already had it. The figure from the book that shows us the mechanism of the allylic bromination. So in our initiation step, we're using the energy from light to cleave the sigma bond between nitrogen and bromine. In general, sigma bonds between two heteroatoms, especially heteroatoms with lone pairs on them, are weak bonds, and so we can cleave that bond pretty readily in a homolytic fashion with light, generating this succinimiddle radical and the bromine radical. The fate of this succinimiddle radical is relatively unimportant because we don't make very much of it. It's only formed in the initiation step. So we don't really need to worry about what happens to that succinimiddle radical. But once we have a bromine radical, that bromine radical is able to abstract a hydrogen atom from our cyclohexene, and it's going to abstract the hydrogen atom that is involved in the weakest carbon-hydrogen bond, which, as we just learned, is the allylic carbon-hydrogen bond. And that's due to the fact that we formed this resonance-stabilized allylic radical, okay? So we could draw another resonance structure. You notice they mentioned here that they only drew one of the Lewis structures, but we do have a second resonance structure that we could draw. Okay, so then we're going to form HBr as a byproduct, and that is a byproduct in this reaction. And once we have our allylic radical, that's going to react with Br2 to give us our final product and regenerate the bromine atom or the bromine radical. So these two propagation steps are the same as the propagation steps in the regular bromination, the regular radical bromination reaction that we learned earlier. So you're probably wondering, where is the Br2 coming from? Well, they give us a hint here. They say that it comes from NBS. And we did tell you back in chapter 10 that NBS can react to give a small concentration, a low concentration of Br2. We're not going to draw curved arrows to show how that happens, but I will draw in general the process here on the board. So the NBS is going to react with HBr. And remember that HBr is formed in the first of our two propagation steps. And we have a substitution process. We're not going to draw a mechanism for it because there's more than one possible mechanism, and we don't really need to know that mechanism to understand the allylic bromination reaction. But what happens is HBr reacts with NBS to give succinimide and bromine, or Br2. So it is vital in this reaction to have a low concentration of Br2, okay? Think back to chapter 10 and ask yourself, what reaction did we learn in chapter 10 with an alkene and Br2? We learned that you can halogenate a double bond. So if we have a large concentration of bromine, we're going to do a direct halogenation of that double bond. Remember, it's an anti-addition. And we'll end up with the trans dibromide. That's chiral. So we're going to form the enantiomer as well. So if we have a large concentration of bromine, this is what will happen. We need a low concentration of bromine in order for the radical reaction to proceed instead of the polar or the non-radical reaction, okay? So that's where NBS is vital in this process. It allows us to only generate bromine as we start to form HBr, right? So the bromine is only going to form from the NBS once we start to generate HBr in step 1 of our propagation process. And so that ensures that we'll continually have a low concentration of Br2, allowing the radical reaction to proceed as opposed to the polar reaction, okay? So that's the radical halogenation A couple of other aspects of this reaction. You'll note that this is a chiral molecule. We didn't draw any stereochemistry, but you would form this product as a racemic mixture. And with our cyclohexene, if you look on the screen here, you can see that if you were to draw that second allylic radical resonance structure, it would be equivalent to the first one. So when we have an allylic radical where the two resonance structures are equivalent to each other, then we're only going to get one constitutional isomer. We're going to form that constitutional isomer as a racemic mixture, but we will only have one constitutional isomer. But if we have an allylic radical with two different resonance structures, then we have two different constitutional isomers that can form. So let's take a look at what happens if we use 1-butene. So first, we're going to generate our allylic radical, and then we can draw our resonance structure. Okay. And now, remember, we only have one allylic radical. There's only one species here. We don't have an equilibrium between these two. These are just two resonance structures showing us that that one allylic radical has spin density on two different carbons. So it can react with bromine to give us the bromine at carbon 3 in this particular case, or it can react with bromine to give us the bromide at carbon 1. Okay, and there's no major product in this particular case. Usually when we have these two different resonance structures, we end up with roughly a 1-to-1 mixture of them. Okay. In this particular case, the product on the left is chiral, so we would form that as a racemic mixture. The product on the right is achiral. So you could say that we would get a 1-to-1 mixture of these two species, but this would be further divided into its two enantiomers. So I guess you could say a 2-to-1-to-1 ratio if you're counting the enantiomers as separate products. But the general rule of thumb is that you would obtain both possible products in roughly equimolar amounts when you have an allylic radical with two different resonance structures. Okay? All right. So our next topic is going to be the oxidation of unsaturated fatty acids. We talked a little bit about this back in chapter 12 when we were talking about the reduction of the partial hydrogenation of vegetable oils. So we just learned that allylic carbon-hydrogen bonds are slightly weaker than other sp3 carbon-hydrogen bonds. And so if we expose an alkene to oxygen, because oxygen is a diradical, as we see it right here, that oxygen atom can abstract a hydrogen from one of the allylic carbons of our alkene, generating a resonance stabilized allylic radical. Okay, and then we typically don't see two radicals coupling to each other. We've told you that they are that process is not favorable generally because radicals are usually present at very small concentrations. But oxygen is present in a very high concentration for a radical. About 20% of the air is oxygen. So there's enough oxygen present if you have an alkene in the air that the allylic radical generated from that alkene can find another molecule of oxygen and generate a peroxy radical. And then that peroxy radical is able to abstract because oxygen's a diradical, when it reacts with the allylic radical, we still have an unpaired electron. And so that peroxy radical abstracts a hydrogen atom from another unsaturated fatty acid, generating a hydroperoxide and a new allylic radical. So you see that steps 2 and 3 are propagation steps. And so this is a chain reaction. And it results in the oxidation of these fatty acids. These hydroperoxides can be converted into other oxidation products. We're not going to go into that. But the point here is that this is how unsaturated fatty acids, oils, vegetable oils, such as olive oil, for example, this is how those products go rancid. These hydroperoxides have a bad odor to them. They have a bad taste to them, or so I'm told. I've tried not to taste rancid materials, but this is how vegetable oil products go rancid. And so this is the reason why consumer products companies will reduce, or at least partially reduce, the unsaturated fatty acids to reduce the number of allylic carbons present in those molecules to slow down that oxidation process, the process by which they go rancid. This also tells us that if we keep our vegetable oil products away from air, then we can prevent them from going rancid. So if you have little vials of olive oil that you're trying to keep from going rancid, if you wrap them up very tightly so that air is not getting in, if you store them cold, you're going to slow down the rate of this process. So these are some ways that you can preserve your olive oils. Okay. So that's one way that we can prevent the process. So the partial hydrogenation, of course, removes allylic carbons, and then when it's not an allylic CH, then the activation energy for step 1 is going to be significantly higher, and so it's going to be much, much, much slower. Your saturated fatty acids would undergo this process much, much, much slower than your unsaturated fatty acids would. Okay. There's another way that you can prevent this kind of decomposition, this kind of oxidation, and that is to use an antioxidant. So an antioxidant is a compound that inhibits the air oxidation of chemicals. And since the air oxidation process is a radical process, antioxidants will inhibit radical reactions. What they will do is they will intercept a radical intermediate and react with that radical intermediate to form a more stable radical. And that more stable radical is going to be less reactive. So you slow down and in some cases stop the radical chain reaction. So let's take a look on the screen at an example of an antioxidant. If you're the type of person who looks at food labels, you've seen BHT as an ingredient in many different foods. BHT stands for butylated hydroxytoluene. This is based on a nomenclature system for benzene type compounds that we'll learn later on in Chem 352M. But what happens when BHT encounters a radical, that radical can abstract the hydrogen atom on the oxygen, extract this OH hydrogen. And what we get when we do that is a highly resonance stabilized radical. Okay, you can see that that radical is going to be delocalized onto 3 different carbons in the benzene ring. And each of those carbons, it would be a tertiary radical. Okay, so we generate a highly stabilized radical, both by resonance and by substitution. And so that radical is less reactive. It's also less reactive because of steric hindrance. You have these bulky tert butyl groups that are shielding this oxygen, that are shielding the radical when it's on the carbon. And so due to sterics as well as resonance, this radical is quite unreactive. So if you have air oxidation going on and you generate one of those alkyl radical intermediates, BHT, if it's present, can intercept that, and then you end up with a radical that's stabilized and is not participating in a chain reaction. So that's how BHT preserves freshness in foods by inhibiting the air oxidation of any oils that might be present in those foods. BHT is an example of something we refer to as a biomimetic compound. Okay, so biomimetic means something that is mimicking a molecule or mimicking some chemistry that occurs in nature. Okay, many times organic chemists draw great inspiration from the chemistry that takes place in nature. And the chemist who designed BHT is a synthetic molecule. It's not a naturally occurring molecule. The chemists who designed and synthesized BHT were inspired by the structure of vitamin E, or alpha tocopherol. You see that vitamin E has a highly substituted benzene ring with an OH group on it, similar to what we have in BHT. Vitamin E is a natural antioxidant. It has this long nonpolar tail that allows it to insert into cell membranes. And what it does in cell membranes is it protects the phospholipids in those cell membranes from oxidation by O2. Okay, if you have any double bonds, if you have any unsaturated phospholipids, then you're going to, those are going to be susceptible to air oxidation. But vitamin E will be able to intercept radical intermediates in that process in the same fashion that BHT does. This OH hydrogen gets abstracted. We get a resonance stabilized radical. It's going to be delocalized on this carbon, and that carbon. And so in that way, vitamin E will inhibit air oxidation. Okay, so that oxidative damage to phospholipids is a natural consequence of the aging process. And so vitamin E can help slow down the aging process. It's not reversing it, of course, so we can't do that. But it is slowing down the aging process by protecting the phospholipids in our cell membranes from damage. All right. So the next reaction we're going to talk about is related to something we learned in chapter 10, and that is the addition of HBr to alkenes, or the hydrohalogenation reaction. Okay, so we learned that if we take an alkene such as 1-butene and we react it with HBr, according to Markovnikov's rule, we generate the more substituted bromide. Okay. But in 1929, there was a chemist named Morris Kharash. He was a Ukrainian immigrant who was working at the University of Chicago in 1929. And he was studying this reaction, and he found that it didn't always give the more substituted alkyl halide. That sometimes it would generate the less substituted alkyl halide, and sometimes it would generate mixtures. So he was confused. The reaction was not giving reliable and reproducible results. Sometimes it would give 2-bromobutane, sometimes it would give 1-bromobutane as the product, sometimes it would give a mixture. So he was trying to figure out what was going on, and he discovered a key bit of information, which is that when his alkene was purified, when he rigorously purified his alkene before the reaction, he always generated 2-bromobutane. So that taught him that there must be an impurity in some of his samples of the alkene that would be promoting the generation of the 1-bromobutane. Okay? So he did some more investigating, and he discovered that the impurity that is promoting the 1-bromobutane or 1-bromobutane is peroxides. Okay? So he found that if we add peroxides to our alkene and then add HBr, that we're going to generate the less substituted bromide. In contrast, if we run the reaction in the absence of peroxides, if we make sure there are no peroxides present, then we would always obtain the 1-bromobutane. Okay? So what's going on? First of all, where are the peroxides coming from? Well, if we go back a slide, the peroxides are coming from air oxidation of our alkene. Anytime you expose an alkene to air, you're going to generate some peroxides. We see a peroxide right here. A hydroperoxide is a type of peroxide. So anytime we have an alkene and that alkene has allylic carbons, allylic carbon-hydrogen bonds, we're able to undergo air oxidation and form peroxides. So if his alkene bottle sat around for a long time, then the amount of peroxides in there would increase, and that would increase the formation of the 1-bromobutane. So once Kharasch figured this out, he discovered that you would just simply add peroxides when you wanted the less substituted bromide, and then you would make sure that there were no peroxides present if you wanted the less substituted bromide. So what's happening? Let's draw a mechanism. Let's go over here to the sideboard, and we'll draw a mechanism for this reaction. Okay. So the first thing that's going to happen is we're going to cleave. Usually we need heat or light. So the book tells you that you can use peroxides, heat, or light for this reaction. And because they say that, I guess we'll allow you to do that. But the reality is, if you were going to do this in the lab, you would need some heat or light in addition to the peroxides, because the energy from the heat or the light is what is going to allow you to cleave the weak oxygen-oxygen bond. It doesn't just cleave spontaneously. You do have to add some energy, and that's going to give you your peroxy, your oxygen-centered radical, and then that is able to react with HBr to abstract a hydrogen atom. So we get an alcohol as a byproduct, and we generate a bromine radical. Okay? So we have two steps occurring in the initiation. Okay, so this is the initiation. Okay? So once we have our bromine radical, that is able to add to our alkene. Okay? Remember we said that radicals tend to do two things. They either abstract hydrogen atoms or they add to an alkene. In this case, we're adding our bromine radical to an alkene, and that is going to generate an alkyl radical. Okay? And then once we have this alkyl radical, that's going to abstract a hydrogen atom from bromine, generating our product and regenerating the bromine radical. Okay. So these two steps are the propagation These are our propagation steps because one of the products of the second step is being used in the first propagation step, okay? So as you look at this mechanism, you can see the difference between the radical hydrohalogenation of an alkene and the non-radical hydrohalogenation of an alkene. In our first propagation step, we're adding a bromine radical to the alkene. And we have two choices. Are we going to add the bromine radical to carbon number 1, or are we going to add it to carbon number 2? If we add it to carbon number 1, as we've drawn it, we generate a secondary radical. If we were to add the radical to carbon number 2, we would form a primary radical. As we know, the secondary radical is more stable than the primary radical, so the secondary radical is formed faster. So the bromine atom adds faster to carbon 1 than it does to carbon 2, giving us the secondary radical. If you remember what happens in the non-radical addition of HBr, we protonate our alkene. And we protonate at carbon 1 to generate the more stable carbocation, okay? So in both cases, radical and non-radical addition to alkenes, we are forming the more stable, the more substituted radical or carbocation. The difference is that in the radical reaction, we're adding a bromine atom to carbon 1. Whereas in the non-radical reaction, we are adding a proton to carbon 1. Okay, so we add the bromine first, followed by the hydrogen atom in the radical process. We add a proton first, followed by bromide in the non-radical process. So that is why we obtain the less substituted bromide from the radical process and the more substituted bromide from the non-radical process. Okay, let's look at a figure on the screen that's going to show us energy differences, delta H's, in these two propagation steps. Radical addition of bromine to ethylene in this particular case. And we see that the carbon-bromine bond we form is a little bit stronger than the pi bond that we're breaking. The carbon-bromine bond is relatively weak as far as a sigma bond goes, but it's still stronger than a pi bond. And then we find that in our second propagation step, the carbon-hydrogen bond that we're forming is stronger than the HBr bond that is breaking. So overall, this is an exothermic process. The two propagation steps are both exothermic. This reaction only works with HBr. It does not work with HCl or HI. The reason is that one of these two propagation steps is going to be endothermic in both cases. So let's look at the bond dissociation energies. In HCl, the bond dissociation energy is 103 kcals per mole. So that's going to impact step 2. If we substituted HCl for HBr, you would see that we're breaking a stronger bond and forming a weaker bond. So propagation step 2 would be endothermic. In the case of the bromination reaction we learned in our previous lecture, that didn't prevent that reaction from becoming feasible, but in this case, it prevents the addition of HCl to an alkene from occurring. Switching step 2 to being an endothermic step prevents this reaction from happening. If we look at what happens with, if we try to use HI, if we look at the bond dissociation energy for a carbon-iodine bond, that is a weaker bond than a carbon-bromine bond, 53 kilocalories per mole, okay? So that is a fairly weak sigma bond. And so what we see, that 53 kcals per mole, that would be the bond that you would form in the first propagation step if you were adding an iodine radical to ethylene. And you see that that carbon-iodine sigma bond is actually weaker than the pi bond in ethylene. So if you were trying to add HI to an alkene by a radical mechanism, step 1 of the propagation would be endothermic. If you were trying to add HCl to an alkene by radical processes, then step 2 would be endothermic. And so that prevents both of those reactions from happening. That is why HBr is the only HX species that we can add to an alkene by a radical mechanism. All right. The last thing we're going to talk about in this chapter is polymers. Okay. So polymers are very large molecules that are made up of repeating units or monomers. Okay. So if we're going to define polymers, large molecules made up of repeating units. So our simplest polymer, our simplest synthetic polymer is polyethylene. So we take a bunch of ethylene molecules, we react them, and they add to each other, and we end up with a long chain. We'll just put an N here in the middle, a very long alkyl chain of all these ethylene molecules added together, and that would be polyethylene. Polyethylene is the world's most popular plastic. So here we have on the screen a picture of HDPE, that stands for high density polyethylene. As you can see, it's used to make milk containers and other beverage containers. The 2 inside of this triangle indicates that it's relatively easy to recycle HDPE. The lower the number, the easier it is to recycle the plastic. And then there's another type of polyethylene called low density polyethylene that is used to make Ziploc bags and other sandwich bags. You see it's a bit harder to recycle than HDPE. Okay? We're going to learn much more about the structures of HDPE, LDPE, and other polymers in chapter 31, the last chapter we're going to do at the end of Chem 352M. Right now, what we're going to focus on in terms of polymers is being able to connect the structure of a monomer to the structure of the polymer that you can make from that monomer. So many polymers are made by addition reactions. And they're made by addition reactions where you have a poly addition, multiple additions. So you have an addition to an alkene, that product adds to another alkene, and so you end up with a polymer. We've mentioned PVC before. Polystyrene or styrofoam is something you're familiar with. So one skill that you need that's fairly commonly asked on standardized tests, such as our final exam, is either given a specific monomer, identifying the structure of the polymer that you can make from that monomer, or vice versa. Given the structure of a polymer, identify the monomer that could be used to make that polymer. So hopefully you know enough about the structure of organic molecules at this point that you would be able to do that. So how do polymers form? Well, there are multiple mechanisms, and when we get to chapter 31, we'll go into more of those mechanisms in detail. But one of those mechanisms is a radical process. So we will show you that one right now. Okay. So we already know that we can relatively easily form radicals from peroxides. And if we do that in the presence of an alkene, and Z could be any kind of group. If we go back to that previous slide, you see that Z could be a chlorine, Z could be a methyl group, Z could be a benzene ring. It could even be a hydrogen if you're just making polyethylene. Okay, so it can be a lot of different things. If we add this oxygen-centered radical to the alkene, then we get a new carbon radical. And if Z is not a hydrogen, right, you can form a more substituted or a less substituted radical. You're always going to form the more substituted radical. And then that radical is going to add to another alkene. If you have a very, very high concentration of the alkene, which you do whenever you're trying to form a polymer, then that radical adds to an alkene. The new radical you get adds to another alkene, and it just goes on and on and on and on and on until the chain gets really long. But then once you start running out of alkene and you start having a higher concentration of radicals and a lower concentration of alkene, then you have a termination process where you have two of those radicals combining to form a sigma bond. Okay. So when you're doing the propagation step, you end up with your Z group on every other carbon. When you perform the termination step, then you end up with your Z groups on adjacent carbons. So what this tells us is that the structures of polymers are not uniform. You're going to have some defects in the chains. You're going to have usually the Z groups on every other carbon, but you're going to have a place where the Z groups are on the same carbon. We also see that you're going to have an ether on one end of your molecule. But these things don't matter because the propagation step usually happens thousands of times for every initiation or termination. Even though you have these differences in your chains and different chain lengths, the bulk properties of your polymers are going to be very similar to each other because the minor differences in the chains are going to be negligible compared to the long regions of those chains that are going to have the regular structure that comes from repeated propagation steps. Okay, so no two polymer molecules are going to be exactly the same, but they're going to be similar enough that their bulk properties will be similar. And we'll have much more to say about polymers next semester, but this concludes our lectures for semester 1. So our next video is going to be the review session for exam 4.